everyone. My name is Marvin Borsdorf. I'm a PhD student at the Machine Listening Lab at the University of Bremen in Germany. In this presentation, I will talk about our recent work with the title Universal Speaker Extraction in the presence and absence of target speakers for speech of one and two talkers. This study was carried out together with my colleague Chenglin and our supervisors, Professor Dr. Haizhou and Professor Dr. Tanja Schultz. In the next 50 minutes, I will talk about our motivation and introduce our universal speaker extraction conditions, which we have defined for our experiments. I will talk about the joint training scheme and describe the experimental setup. Subsequently, I will show the results and give a little discussion on them. And finally, I will sum up our work and highlight some future steps. Speaker extraction can be considered as a subtask in the field of speech or sound separation. And in speaker extraction, we always have a given reference signal of a desired speaker, and the given reference signal is incorporated into the separation process so that the model is able to extract only the target speaker's voice from all other sounds given in the mixture. Speaker extraction was early introduced as frequency analysis approach, but over the time and with the introduction of testnet and conf-testnet, speaker extraction also benefited from those time domain methods. Speaker extraction has been widely studied under multi-talker conditions. That means with at least two speakers in the mixture and with always given present target speaker. However, we think that everyday conversational situations in the real world might look a little bit different, because if you imagine a meeting scenario of multiple talkers, the target speaker could also stop talking for a while or even leave the conversation. And on the other hand, the target speaker could also be the only active talker while giving a presentation or a talk or holding a monologue. There are two recent works which have partially addressed those situations. First, we have XTestnet, which proposes a speaker extraction method which includes multi-talker situations with absent target speakers. And in the FUS paper, there's a universal sound separation method which is investigated, and this method estimates silence for inactive sources. To summarize this, we see that there's a clear demand for universal speaker extraction models, which can be applied to different everyday real-world conversational situations in which the target speaker might be present or absent or be the only active talker. In this work, we propose a new universal speaker extraction approach, which can be applied to multiple everyday conversational situations. For the first time, we describe speaker extraction in 4 different conditions to simulate and cover the aforementioned situations. We propose a joint training scheme with one unified loss function, which is similar to the FOSS approach, which I mentioned on the previous slide. And this unified loss function can be applied to all different conditions and also be used as evaluation metric. And finally, we perform several experiments on different training methods to investigate our approach. If we expose a speaker extraction system to real-world conditions, the application always has to provide reliable outputs in all different situations. And therefore, we formulate our speaker extraction task in 4 different subtasks as follows. You can imagine a meeting scenario of 3 different speakers, speaker A, B, and C, and the speaker extraction task is to attend to the desired target speaker A. The first condition is given by, for instance, the beginning of the meeting scenario, where speaker A and B are actively talking. That means we have 2 talkers in the mixture and the target speaker is present. After a while, the speaker B could stop talking. That means speaker A is the only active talker in the mixture and also the target speaker. And the third condition describes the situation in which the target speaker may stop talking for a while or even leave the room, and speaker B and C are actively talking. And the fourth and last condition is given by the situation in which we have one active speaker in the mixture who is not the target speaker. And we require the speaker extraction system to extract the target speaker's voice if the target speaker is given in the mixture, that means present target speaker, and to output silence if the target speaker is absent from the mixture. I will now introduce our joint training scheme and describe the data tuple adaptation. Speaker extraction has been widely studied in the first condition. That means we have a given audio mixture of two speakers, for instance, speaker A and speaker B, and we provide an audio reference signal for one of the speakers, in this case, a different utterance compared to the audio mixture for speaker A, and ask the model to extract speaker A out of the audio mixture. And for this, we provide the single utterance of speaker A without the other speaker information or audio signals as ground truth signal. In the single talker condition with present target speaker, we have one speaker in the mixture, and the speaker in the mixture is our target speaker. So again, we provide an audio reference signal of the speaker in the mixture with a different utterance and ask the model to extract this speaker out of the mixture, and we provide the ground truth audio signal for the speaker. In this condition, the ground truth signal and the audio mixture signal are the same. The absent target speaker conditions are slightly different. In the two talker scenario, we have, for instance, speaker B and speaker C in the audio mixture. We provide an audio reference signal of speaker A, and because speaker A is not part of the audio mixture, we provide a ground truth signal for the absent target speaker conditions, which is silence. And the same applies to the condition in which we have just one speaker in the mixture. So we have, for instance, speaker C in the mixture. We provide a reference signal of speaker A, but because speaker A is not part of the audio mixture, the model should output silence. And this is indicated again by providing silence as ground truth. Next, I would like to talk about the metric stabilization. In our work, we consider the scale invariant signal to distortion ratio, as it is commonly used in speech separation or speaker extraction tasks, but also, for instance, in speech enhancement tasks. The standard SI-SDR equation is given in equation 1, but commonly a little stabilization value epsilon is used and introduced to this equation to prevent the equation from breaking. This leads to equation number 2. The problem is that in our experiments, we define the ground truth as silence, which means that the ground truth is provided as 0. And this would lead to the fact that equation number 2 becomes a constant value. And this is something which is undesired. Therefore, we move the stabilization value epsilon inside the logarithm from the second term to the numerator of the first term. And this leads to equation number 3, which is similar to the equation in the proposed FUS paper. Equation number 3 preserves the stability criteria for ground truth values, which are 0, but reflects the reconstructed signal in the loss calculation. And therefore, we introduce this equation number 3 as silence evaluating SI-SDR, or in short, SE-SI-SDR, because we can actually assess and evaluate the reconstructed silence signal. The differences between equation number 2 and equation number 3 are small and in the order of 1 times e to the power of -5, which is insignificant for our work. In the training phase, we apply the negative SE-SI-SDR. And for the final evaluation of our trained model, we apply the standard SE-SI-SDR as given in equation number 3. In our experiments, we utilize the SPECS Plus architecture, which is a recently proposed time domain speaker extraction architecture. And we adapted the Wall Street Journal zero-to-mix extraction database according to our 4 described conditions. Since our conditions share the same audio data, we simulated the database in 3 different variations. The first one is given with 100% PT and 100% AT. That means we have the same input mixtures for the present target speaker conditions and absent target speaker conditions, but the reference signals and the ground truth signals are different. The second one is given with 100% PT and 50% AT, in which we have a reduced amount of absent target speaker condition data. The third one is given with 85% PT and 15% AT disjoint. That means we randomly removed 15% of the present target speaker condition data and simulated the absent target speaker condition data out of those 15%. And therefore, we have different input mixtures for the present target speaker conditions and for the absent target speaker conditions. In the training, we started with the baseline model and applied a stepwise adaptation to the different conditions and incorporated different database compositions into the training phase. The evaluation was done on each condition individually. This slide shows the results of our experiments. In the table, we report the speaker extraction performance in terms of SESI SDR in dB for different models on all 4 individual conditions. The higher the SESI SDR, the better the performance. The baseline model was trained on the usual condition. That means 2 talkers in the mixture and present target speaker. We can see that the model fails when it is applied to the other conditions. On the 1T PT set, the model extracts parts of the target speaker or a noisy, unintelligible signal. On the 2T AT condition, the model extracts a random speaker. On the 1T AT condition, the model extracts noisy, unintelligible signals. This shows that the SESI SDR penalizes extracted speech or noise in the same manner when the model is actually meant to output silence. If we add single talker data with present target speaker to the training, this improves the performance on the 1T PT condition, and the performance on the other conditions stays similar. Adding absent target speaker to the training helps in general to improve the performance on this condition. That means adding 2T AT data to the training helps to improve the performance on the 1T AT condition and vice versa. Surprisingly, adding absent target speaker data to the training also improves the performance on the 1T PT task, even if the condition is completely different. However, we see a clear and huge drop in the performance on the initial source task after adapting to the new conditions. We also found that the model sometimes extracts silence, even if the target speaker is present in the mixture. This is undesired since our main goal is to remain stable on the initial source task. If we reduce the amount of adaptation data for the absent target speaker conditions, we encounter a performance degradation on the new conditions. But the performance on the initial task remains more stable. This becomes more prominent if we use the disjoint data composition shown in the results for Model 7. We assume that this is not only due to the further reduced amount of absent target data, but also because of the fact that the mixtures in the present target speaker and absent target speaker conditions are different, and this might reduce the model confusion during the training. To sum up, we proposed a universal speaker extraction approach, which can be applied to different settings in which we have a single or a multi-talker condition with present or absent target speakers. We also introduced a joint training scheme with one unified loss function, which can be applied to all conditions altogether and also be used as evaluation metric for each individual condition. We showed that we only need a little amount of data to adapt to the new conditions, especially for the conditions in which we have absent target speakers. And we also found out that the model occasionally extracts silence, even if the target speaker is present in the mixture. In your future work, we will further study of how to apply classification approaches to assist the model's decision of whether the target speaker is present or absent in the mixture. And we will also examine other metrics to incorporate into our approach. Thank you very much for your attention, and I'm looking forward to have a nice discussion with you.
Okay, thank you, Marvin. I see Marvin is online. Do we have any questions from the audience? Not yet. Then I'll start with a question from online. So there's a question, he's asking, I think the task is suitable for telephone communication environment. Is that right?
Well, I'm not quite entirely sure what is meant with telephone communication environment in that consensus, but I don't think there's limitation for such kind of environment. Should be fine if the conditions match to our defined conditions, and in general, then yeah. But maybe I need some more information on telephone communication environment in this context. But yeah.
Yes, usually in a telephone call, often you have already several separated participants, right?
Yeah.
But there might be some speech in the background. Further question? Another question?
Mm-hmm.
Yes. So the next question is, why are you using scale invariant loss for training, although you would want to keep the scale information to be able to detect absent speakers at the output? Have you compared systems trained with and without scale invariant losses?
Yeah, thank you. That's a good question. To be honest, we didn't think about that so far for the first question. But for the second one, we're currently investigating some other approaches where, for instance, use the MSE loss or MIE loss to go different ways and combining different loss information and also comparing those results. But so far we tried, for instance, the MIE loss, but this didn't work out. And then currently we're working some hybrid things. But yeah, but for the first part, we didn't think about that so far, unfortunately. But that's a good point, maybe for the future steps.
Okay. Next question. Is there anything from the audience so far? Otherwise, I continue with online questions. No? Okay. Related to the previous question, wouldn't it be beneficial for the model to scale all output signals down, i.e. close to silence?
Well, I don't see any benefit on doing this so far. I mean, we already encountered the problem that I think the biggest problem is so far that the model sometimes starts to extract, for instance, some silence, even if we have a usual two-talker scenario with present speaker. And I'm not entirely sure whether this wouldn't be make it harder. But yeah, we could try that, for instance. But yeah, I don't see really the benefit right now from this point of view.
I'm not quite sure how this question is meant. I think it's not meant that you scale down the output, but that the system during the training scales itself all outputs down, whether that problem occurs.
Sorry?
I'm not sure how this question is meant, but maybe it is meant that during the training, the system tries to scale everything down.
Oh, well, didn't find that in the results, but we didn't really investigated that.
Okay. No questions from the audience? There's maybe time for one more. Do we have one?
Yeah,
I have one.
So what is the ideal output in your table? Would it be 0 dB if the
I have to admit that it's hard to explain and assess if you have a negative SIR for the absent target speaker condition. But theoretically, the best result for the absent speaker conditions would be 0 dB. So we start with, let's say, -180, and then because actually we would like to have to output silence, which is 0, but the model extracts, for instance, parts from one of the speakers or artifacts or noise. And in the best case, the output for the absent target speaker conditions would be 0 dB, because in that case we would have inside the the SISDR would become 0, because we do not have any distortions in the extracted or output silence. This would be the best case.
You mean 0 dB of the output level, or the SRD?
The ratio. The actual signal, if we have absent target speaker conditions, is 0. And if we have the ratio between 0 and something which is extracted, this is always like smaller than 0. But in best case, we would output 0. That means the fraction would only consist of the stabilization value in the numerator and denominator, which would be 1, and then we would have 1 inside the logarithm, which would be 0, and therefore we would have an SISDR of 0. And this would be the best condition for the absent speaker scenario.
Okay, thank you. Then let's thank the speaker again.